would convert that dye and oxidize that dye into a compound that has a color that can be measured by absorbance. Okay, so the absorbance measurement of the MTT assay would tell you how many cells are alive. Okay, so if you frame your question that the null hypothesis is drug A, meaning that the group A of wells have decreased viability of the cancer cells compared to the control media, the group B of wells, after incubation for 48 hours. Okay. So I'm asking, because I know ahead of time that drug A is only going to inhibit the cancer cells. Okay, it will not stimulate the growth of the cancer cells. Okay, so meaning that if there is a difference, the difference can only be lower. It can only suppress the growth of the cancer cells. So therefore, I'm asking a one-sided question. Okay, I'm not asking whether it's different or not different. I'm asking whether it is decreased or not decreased. Okay. So in this case, if I frame the null hypothesis this way, that drug A has no inhibitory effect on the viability of the cancer cells, then if I reject the null hypothesis, then the alternative hypothesis would be drug A decrease the viability of the cancer cells compared to the control medium. What if I have no information about drug A? Okay, I just happen to come across this compound, this drug A. I have no idea what it's going to do to the cancer cells. Okay, by all means, it can even stimulate the growth of the cancer. I don't know. So the experiment that you do, then your null hypothesis is drug A has no effect on the cancer cells after incubation for 48 hours. Okay, because I do not know whether the drug is going to increase the viability of the cancer cells, stimulate the growth of the cancer cells, or whether it's going to inhibit the cancer cells and decrease the viability of the cancer cells. So if I frame the question this way, the null hypothesis is drug A has no effect on the cancer cells, okay? And if I reject the null hypothesis, the alternative hypothesis is drug A affect or do have an effect on the cancer cells after 48 hours compared with the control media. But that effect can be a positive effect or a negative effect. So p-value, I'm 95% sure. So the p-value, less than 0.05, okay? Meaning that there's less than 5% chance that I am wrong. If the p-value is less than 0.01, means that I have less than 1% chance that I'm wrong. So this is based on the kind of errors in statistics. If the truth, here we have the truth, okay, whether it is truly no difference or truly there is a difference. Okay. And the conclusion from the test that we have performed. If the test tells us that there's no difference, and there is indeed a difference, then we have committed a type 2 error. If in fact there is no difference, but the test is telling us that there is a difference, then we have committed a type 1 error. Okay? Alpha is the probability of committing a type 1 error. And by convention, we accept a alpha of 0.05. Okay? Meaning that if the test tells me that there is a difference with an alpha of 0.05, that means I am 95% sure that I'm right. So how sure are you that you have not missed any real differences? That's what beta comes in. Okay, so if your test telling you that there's no difference, but in fact there's a difference, that you have missed, your test have missed finding the real difference. What is the probability of that happening? The acceptable or the convention is to use an alpha of 0.2, meaning that whatever that you do, whatever experiment that you do, need to have a power of 80%, meaning that you are at least 80% or more that you're sure that you have not missed any real difference. If you do an experiment comparing group A and group B, you ended up with an alpha of greater than 0.05, okay? So you cannot conclude that there is a real difference. But your alpha, but your beta is greater than 0.2. You have less than 80% power. So then no real conclusion can be drawn. Then you have wasted your time. You can neither say that A is different from B, nor can you say that A is different from B, and A is not different from B. So you ended up having to repeat the experiment with a larger sample size. You wasted your time. So what is the statistical power of the study? So power, beta, alpha, sample size. If I do not find any difference, how sure am I? Okay, this is very important in animal protocols, in clinical study protocols, okay, because we're dealing with lives, very important. We can waste money, well, hopefully not, but it would be very unethical to waste life. Sample size calculation. There are many sample size calculators, and SPSS has a package for sample size calculation, but you have to pay extra for that. But there are many sample size calculators on the internet that is accessible free of charge. And here is one of such link. There are many other websites as well, but this is just one of the websites that I happen to come across and I like. And also at that website, there are many other statistical tips and discussions as well. A very helpful website. The multiple testing problem. When we set a p-value threshold, okay, for example, 0.05, okay, we're saying that there is a 5% chance that the result is a false positive. In other words, although we have found a statistically significant result, in reality, there is no difference in the group means. Well, 5% is acceptable for one test. Okay? If we do a lot of tests, then this 5% can result in a large number of false positives. Now, for example, if there are 200 spots on a gel, and you're comparing 200 spots, and you're making 200 comparisons, and we apply the ANOVA or t-test to each one of them, and because you are accepting 0.05 as the alpha, okay, meaning that you have a 5% chance that you're wrong. Okay, if you have a 5% chance of being wrong in each time and you're doing that 200 times, then you may end up with 10 wrong answers. Is that 10 wrong answers acceptable to you? That is the question. So the level of significance, how many different hypotheses are we examining? How many comparisons are we needed to answer the hypothesis? And are there interim hypotheses planned? All these questions would need to be considered when we pick the cutoff value for the p-value. Instead of 0.05, it might need to be adjusted based on how many comparisons or how many tests you're performing. Now this would be a big issue when you're doing microarray experiments. When you're running a microarray experiment, okay, after treatment with drug A and compare that with the control group, okay, but you're dealing with like 50,000 genes, you're making 50,000 comparisons. How are you going to correct for the false discovery? How do you know what you have found is indeed real? The level of significance in multiple tests, okay, how do we correct for that? The most conservative way is to divide by the number of comparisons. Like for example, the p-value is 0.05, okay, if you're doing 5 comparisons, okay, you divide that by 5 and you consider p-value less than 0.01 to be significant. That's the most conservative way, okay, but there are formal methods. For example, Bonferroni is one of the methods that is frequently used to correct for multiple comparisons. And for interim analysis, the O'Brien-Fleming boundary method or the Land and Demitz analog method can be used to determine the alpha value to determine your result, whether it's significant or not. But when you're dealing with like 50,000 genes, like if you take your alpha of 0.05 and divide it by 50,000, my God, that is pretty impossible. Then you may end up doing the microarray and finding no statistical significant difference. What are we going to do in this situation? Then we have to make a compromise. The false discovery rate, or FDR control method, is a statistical method to control for multiple comparisons. It's designed to control the expected proportion of incorrectly rejected null hypotheses, of the false discoveries. Now, less stringent control over the false discovery compared to the family-wise error rate method, such as the Bonferroni correction, which seeks to